Good afternoon, everyone. We're going to get started here in about 3 minutes. Just wanted to let you all know, so sit tight. We'll be starting shortly. All right, good afternoon, everyone. Thank you for joining us. You are here for the research results presentation for the study Optimizing the Effective Use of RAP in Local Roadways. This project was co-sponsored between the Ohio Department of Transportation and Ohio's Research Initiatives for Locals. It was conducted by Dr. Munir Nizal of Ohio University. For those of you who are participating online, please mute your telephones. Please do not place your phone on hold. If you do that, your hold music will supersede all of the audio of the presentation. This is being recorded, so if you enjoy it, you can watch it again later, or you can share the information with your colleagues who weren't able to make this. The final report is currently being published. It will be available on the ORIL and the ODOT Research website. We are going to hold all questions until the end of the presentation, and then Dr. Nizal will be more than happy to answer them. For those of you online, on the left-hand side of your screen, there is a chat pod. You can type questions there as the presentation is occurring. But with that, Dr. Nizal.
Okay. Thank you, Vicky. Good afternoon, everybody. So So this is the final presentation for the project on optimizing pavement, optimizing the use of RAP on local roads. I would like first to acknowledge my co-author, Dr. Sangsu Kim and Dr. Ala Abbas. I would like also to thank Audit and the Federal Highway Administration for sponsoring this project. I would like also to thank the Technical Advisory Committee. They are listed here. Special thanks to the City of Columbus staff and the City of Columbus for also allowing us to construct the test sections in the city. And I would like also to acknowledge Vicky for her time and assistance through that project. So this is the outline for my presentation. Reclaimed asphalt pavement or RAP have been used since the 1970s in the United States. I would say during the past two decades there was a growing interest in increasing the use of RAP, mainly because of the cost saving that can result from that. Give you an example, in 2017, the National Asphalt Pavement Association reported a saving of over $2 billion for using RAP in new asphalt fixtures, and basically the average use was only 20% RAP. Of course, RAP, the use of RAP has also environmental benefits as it's a recycled material. The biggest problem, of course, is that the use of RAP might make the mixtures more prone to cracking, and basically, therefore, local public agencies and DOTs have been reluctant to increase the percentage of RAP in their new asphalt mixture. To address this problem, there was a lot of research, studies by DOTs, as well as studies that were done by the Federal Highway Administration. But most of those studies focused really on highways and interstates. And basically, those mixtures are different than the ones being used on local public agencies. So there was a research need to address this problem and basically try to see if we can increase the percentage of RAP in new mixtures on local public agencies. So the project had several objectives, and basically starting with the first objective was really to assess what is the current practice for using RAP in surface coarse mixtures on local roads. Before this study, there was really no clear vision about how much RAP is being used and how RAP is being incorporated in new asphalt mixtures. And very important thing is that our study focus was only on surface coarse mixtures. So everything that I will be talking about is only regarding the surface coarse mixture. The second objective, which was the main objective of the study, was to develop a method for designing a cost-effective, well-performing and durable mixes with different percentage of RAP. The target was actually to go to up to 50% RAP, and also provide recommendation for quality control and quality assurance during construction and during paving of those mixtures. And the last objective was evaluate the cost benefits of increasing the percentage of RAP in new asphalt mixtures used on local public agencies or LPA. So the study was divided into two phases. I'm showing here basically the tasks that we conducted in phase 1 and in phase 2. So just focusing a little bit on phase 1. Again, phase 1 and phase 2 each were all about 1 year long. The first task was conducting literature review and basically conducting a survey of local public agencies in Ohio, basically to identify the current state of practice for using RAP in surface course mixtures on local roads. And then we had also a task to develop a mix design for mixtures with different RAP percentages, and also develop a recommendation for a QC/QA for those RAP mixes, performing cost analysis to determine what will be the benefits, and basically make recommendation for phase 2, and finally providing an interim report for phase 1. So the survey was conducted in January of 2017 and 2018, I'm sorry, and basically it had a lot of interesting results, but I think the most interesting was this. Because of time, I will just limit it to one slide. And basically, this slide is showing what is the percentage of RAP being used on local roads. And again, that's according to the survey response, which was conducted, I would say, 2 years ago. So the first thing is that we see is that we have about 1/3 of local public agencies currently do not, or at that time at least, they did not use any RAP in their mix. And then basically 25% didn't really know how much RAP was being used. And what we have also seen is that the maximum was about 25%. Some was a little bit higher, but mostly it was 25%. But again, you do not really see much of those people. Less than 7% really, or less than 8% are using that amount in the surface course for their basically on their local roads. So therefore, the next step was really to conduct a comprehensive laboratory testing program, and based on that laboratory testing program, we wanted really to develop the mixed design approach, or a new mixed design approach. The laboratory testing program was to design asphalt mixtures with different RAP, and I'll be presenting in a moment what the percentages that we use. Just the same way that it's typically used, which is used on local public agency, which is using the Marshall design method, and that's basically determine the asphalt content. And then we did a comprehensive evaluation of the performance for durability, cracking, as well as a rutting. We looked into the different mixed designs, and basically we selected one that we have seen that is being used typically for a surface course on different local roads. And basically what we have done also, we used 2 different RAP materials. We used a virgin asphalt binder in the control, which is a virgin asphalt mix, as well as the 20% RAP, that is PG64-22. The virgin asphalt binder that was used for the mixes, the other mixes with more than 25% was a softer binder with a PG64-28. And basically this was based on testing of the binder. We obtained RAP from different contractors, and basically based on that we have selected 2 RAP materials, and basically here what we tried to do is we selected RAP materials that their binders have different rheological properties, and you can see that a summary of those properties there, basically the continuous high performance grade and the continuous low temperature grade, and you can see that there is a significant difference. Most of our work was with the first one, which is obtained from Shelley Company, and it was in 2017, Shelley 2017 Pile A. That's the designation for their RAP pile there. Based on the literature, we found that a lot of researchers suggested that when you're going beyond 30% RAP, you might need to use a recycling agent. Based on that literature review, we have identified 3 different types, aromatic extracts, and an example that we have used is hydroline T90, and again, there's other aromatic extracts that are available. Tall oil, we use silver rose, and then basically the triglyceride and fatty acid, basically we use the vegetable oil, which is the soybean. It's the generic soybean that is being used in the market. So, the recycling agent, to determine the optimum dosage, we did a binder testing. Basically, we did different, we blended the RAP with the virgin asphalt binder with the same proportions that we have in the mixture, and basically we use different dosages of the recycling agent, and based on that we determined the doses, the optimum doses that will result in a continuous performance grade for the RAP virgin asphalt binder blend of that meets basically the target virgin asphalt binder continuous grade, which was in this case 67.7 minus 22.2. And this is this graph showing, you know, some of the results that were obtained. Basically, we had the binder tested as, again, the binder blend was tested at different dosages of the recycling agent, and based on that we we determined the optimum dosage. And this is basically the results that we had for the different recycling agent, and you can see that the optimum dosage really varied depending on the type of a recycling agent being used. We tested 17 mixtures. I'm showing in this table all the mixtures that we have. We started with basically the control. I'm showing the control, which is a purely virgin asphalt mix, and then we went to 20, 30, 40, and 50% RAP. And again, the RAP, the virgin asphalt binder for the 30, 40, and 50, just to remind you, we used a softer binder. For the control and the 20%, we used the 64 minus 22. And basically, we, for the 30, 40, 50, we use the different types of rejuvenators or recycling agents that we have used. And then we did also, for RAP2, we did also tested the RAP2 or mixture, the same mixture, but with a RAP2, and that's what you see. We did, again, different testing on the designed mixtures. We did for low temperature cracking, ACCD, or the asphalt cracking, a concrete device. Basically fatigue cracking, we did SCB using the Illinois method, which is commonly referred to as the IFIT. And then basically we did the indirect tensile strength, and we did the modified allotment or the AASHTO 283 for durability. So starting with the phase 1 results. So the SCB parameters, we looked into 2 parameters. The first parameter, which is commonly used, is the flexibility index. I'm showing the definition really of that flexibility index. It depends on the area, basically under the load displacement, as well as the slope of the post-peak curve, which is shown here. Another parameter that we have actually recommended based on a study conducted back in 2017 for audit was the normalized fracture energy. It's basically the fracture energy divided by the peak stress, or basically the strength that is obtained in the SCB test. So I'm showing here the flexibility index, and very important thing that I would like to note is that for the lab, those numbers are for long-term age, and the aging that we have done was through putting the prepared mixtures for 5 days at 85 degrees Celsius. And basically what we can see here is that as you are increasing the RAP percentage, you can see that your flexibility index is lower, indicating that it is more prone to fatigue cracking. What we can see here as well is that although we have used a softer binder in the 30%, 40%, 50% RAP, but this did not really help in improving the fatigue cracking resistance of those mixtures. What I'm showing here is the results for the 30, 40, 50 with the recycling agents, and basically with the 3 recycling agents. And what we can see is that the recycling agents were able really to improve the fatigue cracking resistance of the mixtures with 30%, 40%, and 50%. We can see that in general, they resulted basically in a fatigue cracking that is similar to that of the 20% and the control. We can see that also that the aromatic extract, the hydroline in this case, had a better improvement as compared to the silver road. The soybean showed good results on the short-term aging, but once we did the long-term aging, basically, as you can see, it did not really show the same improvement that we have seen with the recycling agents, indicating that soybean might be a softening agent rather than a recycling agent, which is something important to differentiate. Now, very important, before I go to the next slide, is that the variability of the flexibility index was relatively high. It was between 20 and 25%, and this is something that we have noted in the previous study, and that's why we use basically the normalized fracture energy. The normalized fracture energy, the coefficient of variation was less than 15%, and basically what you can see, it has very similar trend to that we have seen in the flexibility index, and that is something that we have also noticed in our previous study. So this is another parameter that is showing again the same conclusion about if we used a softer binder, fatigue cracking might not be maintained. If we're using the right recycling agent, in this case the silver road and the hydroline, it seems that up to 50% RAP, we will be able to still maintain the fatigue cracking. Very important is that the RAP binder replacement, something that I will be talking about in the second phase, that RAP binder replacement, the maximum that we had was, in this case, was 41% for the 50% RAP. This is how much of your total binder was replaced by the RAP binder. The IDT test results, if you're for the same virgin asphalt binder, if you are increasing the RAP content, you can see that the indirect tensile strength increase. So for example, for the control and the 20% RAP, where we have 64 minus 22, you can see that the 20% had a much higher, or a higher, I would say, indirect tensile strength as compared to the control. And the same, once we go to a softer binder, we can see a drop in the ITS, but again, with increasing the RAP, that drop, we can see that it is increasing. And again, one of the things that we have noticed is that, that you can notice here, is that in general, the different recycling agent did not really decrease the ITS, except as you can see here, there was a little bit of a decrease with the soybean, and again, this is indicating a softening effect of that recycling agent. In terms of the durability or moisture damage resistance, as measured by the TSR, the tensile strength ratio, typically it's required between 70 and 80 depending on what type of mix, and basically, as you can see, it met both, like the 70 and 80, all of those were 80%. In general, using RAP will not result in any moisture damage if your mixture is well designed, meaning that you have really designed it so that you have a good amount of asphalt binder, and basically this is what you see. So again, the TSR for all mixtures were beyond the 80, and basically it met the criteria. For the cracking temperature, this is based on the ACCD. This is the low temperature cracking. Again, what we have noticed is that the virgin asphalt binder, to a certain degree, control your basically your cracking temperature of the mixture. So what I'm saying here is that using a softer binder, using a 64 minus a 28, what we notice is that in general, with using such a binder, we are able to go up to 50% RAP without really affecting the low temperature cracking resistance of the mixture. So using, again, the right virgin asphalt binder will result in a cracking resistance or low temperature cracking resistance that would be equivalent to the control. So the asphalt binder, the virgin asphalt binder, will play an important or have an important effect on the low temperature cracking of your mixture. And again, the recycling agent, the same thing, we're able to result in the same low temperature cracking as that of the control. So both are good. We did also the asphalt pavement analyzer to evaluate rutting because we have seen that there might be some softening. And again, all mixtures have met the criteria, which is the 5 millimeter for mixtures with medium traffic. The only thing here that I would like to note is basically using a softer binder, you can see that it increased the rutting. But again, it is not that significant, or basically in all mixtures they were not really high. The rejuvenator or the recycling agent, to a certain degree, some of them have resulted in a higher rutting, specifically the soybean that you see here. Again, that is an indication of the softening effect of that recycling agent. But again, in general, all of those mixtures in terms of the rutting met the criteria of less than 5 millimeters. So we did a cost analysis, and again, in phase one, the cost analysis was based on prices in back in 2018. So it's very important because the binder cost and even the rejuvenator recycling agent cost have changed since then. So this is based; those results are based on the cost and the prices at that time, which was in 2018, beginning of 2018. And what we have, you can see, is that again, increasing the RAP binder or the RAP content, you can see that there is an increase or a decrease in the cost, and basically increase in the reduction in the cost saving. To go to real numbers, to see how much that reduction is, I'm showing this table. We're comparing it to the 20% RAP mix, which is, I would say, the typical mix that has been used by the local public agency and by the city of Columbus. And then we are also comparing it with a virgin mix. And you can see that we're comparing it to the 20% RAP. You can have a cost reduction up to basically more than 25%. With the hydrogen and soybean, with the silver road, it's around 14%. If we're comparing it to the virgin mix, and this is important because, as I said at the beginning, some local public agencies are not using any RAP. It's about 1/3 that they're not or they're not using any RAP in their mixes. So therefore, that comparison, at the second part of this table is very important for those agencies. You can really go up to close to 40% when you're using a 50% RAP. So the effect of the RAP source, and that was very important, that whatever results you're getting for one RAP, you cannot really extrapolate it to another RAP, and that is very important for this study and for the local public agencies who would like to implement the studies, that you need to look at the RAP. And that's what the results here you can see is that there is a significant difference in terms of the fatigue cracking resistance between RAP 1 and RAP 2 as indicated by the flexibility index. And that result is, again, also for the normalized fracture energy, you can see the same thing. There is a considerable difference between both of those RAP materials. The ITS, there is some difference, but it's not that significant. And again, the TSR, we did not really see. Both are performing well, but there is really no difference in that. For the fatigue cracking, there was a difference, and you can see it here, but it was not as significant as the one that we have seen with the fatigue cracking. And so the findings from phase 1 is that using a softer binder did not really result in it was not able really to overcome the effect of the RAP when we're using more than 30% RAP, and therefore we had to use a recycling agent, the aromatic oil, and basically the tall oil that we have used. Recycling agents have resulted in mixtures with 30, 40, and 50% RAP that have a similar fatigue cracking resistance to that of the control and 20% RAP mixes. We have seen that the aromatic oil and the hydroline had a better improvement and was more effective, specifically when we went beyond the 40% RAP as compared basically to the silver road. The soybean had basically resulted in an improvement. It was comparable to the 64 minus 28 at the 30% RAP, but we can see that basically its improvement was not as significant as those for the other two basically recycling agents. So what we have noticed is that the soybean is really resulting in a softening effect, and therefore it did not improve significantly the fatigue cracking resistance of RAP mixtures when using more than 30% RAP percentage. In terms of cost analysis, if we are comparing to the 20% RAP or the one that is currently used, using hydroline and 50% RAP can result in about more than 26% reduction, as compared basically to the silver road will result in this case 13%. The RAP source has a significant effect on the performance of the asphalt mixtures. So basically, no two wraps should be treated the same, and therefore it is very important for those agencies that are planning to implement the results of this study. It is really important that the wrap binder should be basically characterized in order for you to use a wrap more than using a wrap percentage more than 30%. So it is really important to quantify and characterize the properties of the wrap binder. This is the recommended mix design, and again we are in our mix design, rather than using the wrap percentage, we are using the RPR, and this is something important, because when we went to the field, we found out that your 40% wrap can result in a different binder replacement ratio. And at the end of the day, it is the most important factor is that how much of your binder in your mixture being replaced by the wrap binder. This is the most important. It's more important than the wrap percent itself. So we are in here. We're using the RBR, and just to remind you, the RBR is the wrap binder replacement. If it is more than 0.25 or less than 0.25, it is less than 0.25. Then basically you need to use your a binder grade that meets basically your target binder grade. Should be you using this equation to determine that. If you're using higher, then you need to use a recycling agent. Based on our results, the aromatic oil and the tall oil are the ones that we did the testing on, and basically they performed well. But again, this mix design allow you to really use any recycling agent as long as you're meeting a criteria. So we did our testing for 2 types, but this doesn't mean that those are the only types that can be used. And basically this is the most important, that once you determine your optimum dosage, then basically you need to do the performance testing. We are recommending certain tests. We are recommending basically the SCB and the flexibility index for those tests. We did some preliminary testing on the IDL test or the CTI, but at that time, it was back in 2018, that test was new, so we did not really provide a limit. So the flexibility index and the normalized fracture energy are the ones that we're using for the fatigue cracking, as well as the ITS. Durability is based on the TSR, and rutting is based on the asphalt pavement analyzer criteria. So if it meets the criteria, then basically whatever the design that you had in the volumetric based on the Marshall method can be used. If it does not, then you need to change either your recycling agent dosage, or you need to change your asphalt binder. And basically the contractor has to work out this so that they will be able to meet the criteria. And this is the criteria based on our testing. Very important thing that I'm showing here is that the SCB test results are based on long-term age samples. We did it based according to the AASHTO R30. There are new test methods, and again, if needed, then there should be a validation of those methods and comparing it to the ones that we have. And basically we have the TSR 0.8, the rutting should be a maximum of 5 millimeters. So phase 2 mainly was to construct test sections. So we did 8 test sections. Those test sections were on Hoare Road in the city of Columbus. And basically the construction was done in September, basically between September 11 and September 21st. Every test section that I'm showing here, basically the 8 test sections, we had 1 day for every test section. The entire project was about 2 miles in length. It extended between Georgesville Road and the Bledsoe Drive. And again, it's in the west end of southwest of Columbus. Basically, that roadway was a two-lane roadway. And basically, we try to have those sections to split equally within those 2 miles. And basically, the layout of those sections are, I'm showing it in the graph here. So we did, first of all, some testing, preliminary testing, mainly the light falling weight deflectometer. And basically, this was done to really determine where the cores should be taken so that we can avoid areas that are showing to be significant deterioration and they are distressed. So basically, we will not take cores from there. This is just the result of the LWD. We did not really see any variation between the test sections in terms of the LWD. Again, there were high and low points, but in general, the test section, there was not really differences that we can see between the test section that will affect the results in the future. So during construction, we have monitored construction, the placement, mainly monitored the temperature. We obtained as well density, and we obtained also core samples. We also made sure that there was no problems during construction, and if there was a problem, we had to notify the City of Columbus inspector. In general, there was no problems during construction. Those pictures that I'm showing here, those are how the rejuvenators or recycling agents were injected. Basically, in this project, they were injected into the asphalt binder just before the asphalt binder went into the drum. And you can see that those are the tanks for the different rejuvenators, and basically they were pumped, and through the foaming device or the foaming hose, this is where it was injected. Again, there was really no problems in terms of the production and in terms of the using of recycling agent. And basically, those are some pictures taken at the asphalt plant to document that. Those are pictures of the sections just after compaction, directly after construction. Again, you can see that there was no problem. Again, pictures here during coring, and basically also that we have done. We did some testing, density testing, as well as light falling weight deflectometer testing after the construction, and also we obtained at least 10 cores from each test section. We did testing on core samples as well as on samples that were prepared using the field mix that were compacted in the lab. The first thing was to do the air void, and then basically doing the ACCD for low temperature, SCB, and then we did ideal. Again, at that time, the construction was in 2018, so at that time, that test was, there was a procedure, an AASHTO procedure there, so we could follow. And basically, those are the different tests that we have conducted. For the lab sample, we did the same exact test, but we also did the asphalt pavement analyzer, because again, we can really, with those mixtures, we can compact and different mixtures with the different sizes needed for the APA. So starting with the wrap, a very important thing is that the wrap that was used in this project, it was a little bit rich in terms of the asphalt binder. It had about 6.1, which is, I would say, higher than what is typically used. Typically, it's about 5 to 5.25. This is the typical, wrap content that is observed in the field. But this one was towards the higher end. I think that wrap was obtained from a job for Franklin County. The high temperature grade was high, it was 86.8, and then basically your low temperature, it was minus 16. Very important thing is that those are the different mixtures that were used in the field. The RAP percentage, the RAP binder replacement was higher than what we have seen in the lab. So for example, your 40% really RAP had the same RPR as those that we have seen in the 50% in the lab. And then basically your 50% RAP had about 0.53 basically RAP replacement binder, which is higher or much higher than the maximum RPR that we have seen in the lab. And again, that is when it comes to the field, you cannot really control those things. So relative compaction, again, you can see that in general, densities were very similar to different sections. There was really, in terms of compaction effort and compaction patterns, didn't change between the different sections, so we were able to achieve the same density with the same compaction pattern. Okay. So the results here are for the field cores. This is the flexibility index. Very important. Those are core samples. So those core samples are short-term aged, I would say, if you want to compare it. And basically what you can see here is, in general, the 30%, for 30% RAP, all mixes perform well, whether it is the softer binder or the recycling agent. But when we went to the 40%, the hydroline had similar results as that to the control, but the silverwood did not really show the same improvement that we have seen with the hydroline. With the 50% RAP, and again, this is where we have about 0.53 RPR, both did not really show a improvement. Basically, they were significantly lower or had a significantly lower flexibility index as compared to the control mix. I would say for the NFE, it's very similar trend that we have noticed, and you can that we have seen with the flexibility index. So both parameters are giving similar results. Again, the only difference is the variability between them. If we are looking at the lab compacted, so those are field produced, lab compacted, we're seeing similar trend as the cores, but the main difference that we have seen is that basically your lab results had a lower, so it is the same trend, but it was lower in value. And again, that might be, as we have, other studies have reported that might be attributed to different things. I would say the first thing is that the lab compaction will not be the same as the field compaction. This is one thing. And then, although we corrected for the thickness, but still the thickness, there was a difference in the thickness between the samples. In terms of the normalized fracture energy, again, similar results that we have noticed. But one thing that I want to mention here is that the values itself was not as, the difference between the values between the lab and the field, lab compacted and cores, were not as significant as with the flexibility index. Another test is the ideal. The main parameter from here is what we refer to as the cracking test index. This procedure have developed by Dr. Fuji from TTI, and basically as part of an NCHRP ideal study. And basically that depends on the fracture energy and also the slope of the post-peak. This test is the same, conducted in the same way that as an ideal test. The only thing is that you have to monitor loads and deformation, and basically you need to basically record them throughout the test. So the CTI the recommended is typically around 150. This is what is recommended. We can see that there is differences in the CTI between the control and the other mixes, but in terms of meeting the criteria according to that CTI value, it seems that it met the criteria of the 150. This is what have been recommended by different studies, including the ones done by the TTI. And for the lab compacted, it's the same, again, same trend, but the only difference is really the numbers are lower, just like what we noticed with the SCB. The cracking temperature, in terms of the cracking temperature, we have noticed that really all mixtures, according to the ACCD test results, basically had similar performance in terms of the cracking. The cracking temperature was very similar, except maybe for the 50% mixtures, especially the hydrogen had slightly lower, but again, it was not that significant. For the lab compacted samples, again, it's the same exact thing, very similar results to the control, and they basically, again, this is an agreement to what we have seen in the lab, which again, the asphalt binder, the properties of your asphalt binder play a major role in terms of the cracking resistance of the asphalt mixture. In terms of the rutting, all mixtures really had a rutting that is less than the 5 millimeter. What you can see here also is that, except for that 40% wrap, all of them had, all the wrap mixtures had lower rutting as compared to the control. But again, all of them met the criteria. So we did the evaluation, and this is basically done last month in April, which was 7 months after the construction. We did not really notice anything. We don't expect anything to happen, at least no failure during the project. So those are pictures that were taken again last April. Was sunny and warm that day, at least. So again, no problems based on the 7 months that we have done. All the sections have, I would say, no distresses and similar performance. But again, this is, this is a very short period to do an evaluation. Cost analysis. So during the construction and basically during the bidding, we obtained that bid unit price for the different sections, and this is in cubic yards. And basically, those one thing that I'd like to note is that the mixture, the unit bid price did not include the price of the recycling agent because it was donated. And therefore, we went back based on the dosages that we used, and basically we added that, and this is what you see here, the total cost. So the total cost reduction, again, based on the bid price, you can see that, with a 50%, you're expecting about 25% reduction in cost as compared to the control, and very important, the control here is the 20% RAP. In the field was 20% RAP. And one of the things that I want to mention here is that the PG64-28, in terms of performance, so far in the field, whether it is the cores or the tests done on the lab compacted field produced, it's showing good performance. But in terms of price for the contractor, it's not worth it because that the cost is less, like cost saving is less than 1%. And the main reason for that is really the cost of that binder, the PG64-28, which is more expensive than the 64-22. So basically the savings is not that much, and that's what you see. We did our own material cost. So we did, based on the proportion there, we did also an evaluation of the cost of the material itself, not the bid. And again, it's very similar to what you see in the bid reduction. Again, you can see that once you go to the 50, you can start seeing a much higher cost reduction in terms of the materials. But again, at that percentages, as a contractors, I think the contractor have there are other things that the contractor might have considered that resulted in basically increasing the cost as compared to only the cost of the material. But in general, you can see a significant cost reduction, again, even with the using a recycling agent, and that, again, depended on the percentage of RAP. What we have seen is the hydroline and the silver road basically have improved significantly the cracking potential for phase 2 and for the test sections, the cracking resistance of the mixes when using a RAP binder replacement of 0.3. We can see that the hydroline had a much better improvement when the RPR was 0.41 as compared to the silver road. But beyond that 0.41, that recycling agent improvement was not significant to overcome the increase in the RAP percentage or to overcome the effect of the RAP on the mixture fatigue cracking resistance. The softer binder, again, with 0.3 resulted in a similar performance to that of the control mix with 0.9 RAP replacement binder. The rotting resistance was enhanced by increasing the RPR in general, even though that recycling agent was used. In general, the flexibility index, the normalized fracture energy, and the CTI had similar trends in the field and in the field cores and the lab compacted samples, but basically the values in the field cores were higher. And again, the cost analysis that was conducted in phase 2 is showing that with a 40% RAP, you can increase or decrease the cost by at least 15%. A preliminary evaluation that we have conducted so far is indicating that the test sections, there is no really issues after 7 months of construction. So what are we recommending? Again, we only monitored those test sections for 7 months. This is not enough really to draw any conclusion. So what we are recommending is that those sections have to be monitored. We have provided in our report a methodology for monitoring those test sections. I would say that those test sections should be at least monitored for at least 5 years. And then based on that, you can draw conclusion about performance and also to draw conclusions about the cost effectiveness of increasing RAP. Mixed design specification were developed as well as the QC/QA for mixtures with different RAP contents. I think if we want to evaluate the feasibility of using RAP, that mixed design should be implemented, and we're recommending that different local public agencies will start using those specifications and to do pilot studies. Based on those pilot studies, I guess there will be a much better data to really help in increasing the RAP percentage on local public agencies. One important thing that we have done limited work on the recycling agent, on the effect of the recycling agent on the mixture performance with different RAP percentages, but I think that there should be further study about that. Our study was limited because of the time, really, and therefore studying the effect of recycling agents, different recycling agents, should be done in the future. Specifically, that we're seeing that the recycling agents are helping to increase the RAP content, and basically mixtures with higher RAP content and recycling agent are so far, based on the initial cost, they are cost effective, so therefore the use of recycling agents should be further evaluated in the future. With that, I would like to conclude everything, and hopefully our roads will always be smooth, just like this road. So, do you have any questions? We start with the...
Is your lab data, is that long-term or is that short-term?
All lab data for phase 1 are short-term. Are you talking about phase 2?
Both.
Phase 1, everything is long-term that I'm presenting here. Phase 2, it's short-term. Everything is short-term because the core samples were short-term. And the long-term aging was done using the AASHTO R30, so 5 days in the oven at 85 Celsius.
Munir, thanks for the great presentation, first off. You mentioned about the bio-based rejuvenator, the soybean, as being more towards a softening. The information seems to indicate it's more of softening. And you identified that based on the long-term aging. With respect to the other two that were used, by virtue of the fact that they, I'll say, maintained their ability to provide persistence against the heat cracking and all those other different properties, does that speak to the longevity of their effect on pavement?
Yes. So that's a good question. So the problem with having so I did not present here, but I think it is in the report. The results of the short-term aged, or results on short-term age sample, actually the soybean, you can see that it had similar to a certain degree results to that of the other recycling agents. But once you go to the long-term, you can see that there is a drop. Of course, all of them will drop once you go from short-term to long-term. But the problem is that with the long-term, with the long-term, with the soybean, it's basically it was more significant. The drop was more significant. And again, like we cannot really tell if it is a softening, like if it is a softening effect, but that is at least what it will be. Now, why we do the long term? Because the long term tries to tell us what will happen after 5-7 years. So initially, maybe the soybean will perform well in the field, but maybe after 5-7 years, then you start seeing that its effect is not as beneficial as the other recycling agents. So it is for the long term. The long term aging is really to again, longevity. So.
Any other questions in the room?
Your cost analysis?
Yes.
I'm assuming they're just based off of cost savings from the material recycling agent is RAP,
Yes.
we considered adjusting them for your performance?
Well, we cannot really, we could not really, again, run a life cycle cost analysis unless we looked at performance in the field.
Well, I'm just saying because a lot of your data shows like 50% RAP is significantly different than 30% RAP or 40% RAP. It goes down, so you would assume the performance just based off the data.
We can, but for this study, we did not. But again, I think, yeah, we can predict, but how much is the prediction? That's again, it's...
Well, it depends on what the minimum value is, which I don't see listed anywhere, but...
For what?
Well, that's what's the recommended minimums.
So for the recommended minimums is, again, for long-term age, we're recommending, if you look at the chart don't have the screen. It's, again, for, if you go to...
Yeah, I have the slide here.
Yeah. But again, this is for the long term.
It's like right before phase 2 starts. Wow.
The question is always is that, they met the minimum, but if something is meeting the minimum, is higher than the minimum, I think that the field should tell us more about that. But again, we did not really include in any of those any performance, and that's why we recommended any recommendation about the cost effectiveness should be based on the long-term monitoring.
So that slide, design acceptance or design in? Just
This is basically for the design. This is for the design.
Specifically, are you referring to when you talk about performance? Are we talking about years here, or are we talking about
testing performance, like the actual physical data to get
The recommended is based, because in the mixed design we would like to do a long-term aged. Because again, for quality control, it's different, but for quality control we did not really recommend SCB, we recommended just the ITS. And basically this is just to make sure that, the mixture is holding up. But for the mixed design, we had recommended to use the SCB, and basically the SCB was based on the long-term age.
So I guess just in theory, there should be a little asterisk by your cost analysis. Those are just based on principal bid prices.
We include that this is initial cost. Like in the recommendation and everything, in the presentation might not, but this is, based on unit bid price. So.
Okay, well, if there are no more questions, we thank you all for participating. The final report for this project will be available online probably in the next month or so. You can go to the website www.dot.state.oh.us/research or http://oril.transportation.ohio.gov to download the report, fact sheet, and a recording of this presentation. If you do have any other questions that you come up with later on that you'd like the answer to, you can send an email to research@dot.ohio.gov, and we will forward it on to the appropriate people to get you an answer. Thank you very much for joining us. We appreciate you all. Have a good rest of the day.